Okay, any other questions? Okay, if there will be only one thing that will remain with you from our first lecture, we are doing quantum mechanics. So that is probably one of the most important things that you have to keep in mind. Quantum field theory is quantum mechanics. So whatever you did in quantum mechanics has an analog in quantum field theory, and whatever we do in quantum field theory will somewhat have an analog in quantum mechanics. So but when you see about the overlap amplitudes, etc., we have the same thing over here in terms of states. One thing that will be different is we will not usually work with states but operators. So that is probably one thing that kind of causes students to think that QFT and quantum mechanics are completely different, because in quantum field theory, almost all the time we will be dealing with operators like A and A dagger rather than the states themselves. So let's continue with this one. I will add those two terms. I have pi squared over 2 plus 1 over 2 omega xi squared, 1 over 2 k xi minus xj squared. Have you ever solved this problem?
I lost it because I had to take from states lecture.
Okay, that's good. That's nice. I mean, I do advise even those doing mathematical physics to take some theoretical condensed matter course.
But that does not include that I remember how to solve it.
Well, so this is a nice opportunity for you to review them. How do you solve the system? It's an exactly solvable system, this one is also. So it's exactly solvable. I mean, you can solve it in classical physics or quantum mechanics, whichever one you want. You will mainly use the same tricks. Try to solve this problem. Now, you see, I can define the annihilation and creation operators using these terms. That's it. Or if you like, the last term also brings an xi squared. I can also combine that with those two terms and just write the last term as minus k xi x. Well, let me not say xi minus xj, but xi minus xi minus 1. I mean, they're all the same thing.
What do you mean by that? What do you mean by that? Aren't you restricting the interaction by?
No. What I mean when I say they are the same thing is this Hamiltonian is this one. What I mean by those two are the same thing. So if you want, when you want to define the A and A dagger operators, you can use these two, or you can use these two. Well, I will use these two. So I will have AI, well, basically I'm using these definitions over here. It's just the X and the P of the I oscillator. This is my AI. Now, if I do that, what I will obtain is my Hamiltonian will be sum over I omega AI dagger AI plus, let's say, some coefficients AI plus AI dagger minus AI minus 1 minus AI minus 1 dagger squared. In my master's thesis, I was studying a Hamiltonian of this form, and when we sent it to a referee, one of the replies of the comments of the referee was that he or she was complaining that we take into account the interaction of each atom with the previous one, but we don't take the interaction of each atom with the next one. So this xi minus 1 takes care of all those interactions. Anyway, let's continue with this Hamiltonian over here.
Hocam chi x I minus squared term, where does that appear?
This one.
Yeah.
It is this one. Because remember, x is a plus a dagger with some coefficient. I'm just too lazy to write down the coefficients. So this is my xi. This is my xi minus 1. So, for example, I have terms of the form minus 2 lambda AI dagger AI minus 1 plus AI minus 1 dagger. I have many terms, but these are just two of them. So what does this tell me? Let's say that I have these many oscillators. I might have these energy packages localized in any one of those. More than one, in fact, in any one of those. And this AI plus AI dagger basically will give me the number of packages I have in one of those oscillators. So I'm just multiplying the number with their energy and summing them up. So this term with the summation will give me the energy of the system if these other terms were absent. Now, what do those terms give me? Well, again, let's look at a system where, let's say I have, this is the ith oscillator, this is the I plus first, this is the I minus first, etc. And let's say at a given moment, I have n oscillators over here, n packages, n particles. Let's say this is at t equal to 0. I can find my state at t is equal to epsilon by, well, basically doing the same thing over here. At a very small amount of time afterwards, I have the same state, 1, but then I have this minus I epsilon h term acting on whatever state I have. But let's see, what kind of terms do I get? If you look at this operator, what that operator does, let me use I0 here. What that operator does is it annihilates, destroys one package at some location, let's say I minus 1, and creates one at the next location, at the ith site. That will be what this term does. So when I act it on this my state at t equal to 0, it will just, it won't do much except when I is equal to I0 plus 1. At that term, it will destroy one of those packages. So I will have n minus 1 packages over here. I will have one more package at the next site. I will have one over here. So this is due to this term. I will have another component in my expansion of my state at t equal to epsilon. That will come from that one. What that does is it annihilates a package at a given site, creates another one on the earlier one. So I will have n minus 1 and 1. So at the time t is equals to epsilon, there is a finite probability that I will find a package at the next site or the previous site. Just remember, my wave function at t equal to epsilon is 1 minus I epsilon h at t equal to 0, acting on t equal to 0, which is ni0. I have n particles at the site I0, minus I epsilon h acting on the same state. But h acting on that one will be, well, there are some coefficients over here. Then I will get another coefficient. I will have n minus 1 particles at the site I0 and 1 particle at the site I0 plus 1, and other coefficients with n minus 1 particles at the site I0 and 1 particle at the site I0 minus 1. Plus, of course, I have other terms. I started by having n packages over here, which I will identify as my particles. As my system evolves at a later time, there is a finite probability that I will have most of my particles still over here, but one particle here or another particle over here. So all of them were here. At the next time, they started moving around. Now I have the motion of my packages. My particles are moving. Why are they moving? Well, they are moving because of this term over there. So that is something I want you to keep in mind. That term gives us the motion of particles. This term doesn't give me any motion. Without the last term, my particles are not moving anywhere. Only the last one causes the particles to move around.
But this theory itself is not indicating any local any local movement, right? We are basically saying that by I and I minus 1, we are basically saying that these adjacent particles will move from one point to the other.
From one side to the others.
We could perfectly say that not I but J, but then the movement will be not like a movement from one side to one side, but just going from one and
Just
all of a sudden to other.
jumping to the other one. Exactly,
So
yes.
This is actually our assumption to this theory. So it's not a local in
Well,
the sense that, right?
Mhm. Well, you see,
It's not the same.
remember, we are just constructing our one dimension. Now, my one dimension is at the moment discrete. So well, that is why I gave you the example from condensed matter physics. There are these atomic chains. Okay, where did I draw it? Anyway, it's an example of an atomic chain, these vibrations. They are called the phonons. But as your friend commented out, well, when we look at space around us, it's not just discrete points. At least within our observations, within the experimental errors we have, the space is continuous, not discrete. Well, at a very fine resolution, it might still be discrete, but as far as we know at the moment, the space is continuous. So now we have to take the limit where this I becomes a continuous variable.
So the next
That will be the next step. This is discrete. The next step, we will take the case, what happens if these points are continuous? Particles, as far as we can tell, they are moving continuously over space. They are not jumping from point to point.
in non-relativistic quantum mechanics of a single particle, the wave function is localized at measurement and then spreads out again when you stop looking at it.
Depends on what you are measuring. Are you measuring
Energy.
the position?
Uh,
If you are measuring the energy, you are not localizing it.
no, but you localize it in, you have a specific energy value.
Yeah, that's not a usually that's not a localized state.
Okay, so in position space, we'd have a localized position, like it's here, it's a spike, like a Dirac delta.
Okay.
Then it spreads out over time. This is analogous to that in a weird way, but there's no connection, right? Because we're talking about a many particle chain.
Well, basically it's the same thing. You see, what I started with saying that, okay, I have all my particles over here.
Mhm.
So if you want to look at this as a one-dimensional problem now, one-dimensional quantum mechanics problem, my wave function is localized at a single point, but it's not an energy eigenstate, so it will spread in time. Or I can look at it from the wave packages perspective. Each package is localized at a given site.
Okay. They all spread. It's
They
the
are
collective
spreading
action
over
of-
sites.
Okay, yeah.
There is something I don't understand with these kind of quantum. For example, you started with some state located at some point, right? And in the
A
Hamiltonian,
package located at a given point, okay.
and in the Hamiltonian, you basically state that the adjacent lattice points will interact with each other.
Yes.
But when you start with some state that is localized at that point, what is there to interact in the adjacent?
Well, no, this is not an interacting theory, by the way.
In the classical sense, I understand this potential.
No, this is, even in the quantum sense, this is not an interacting theory. Interaction terms will be when I have the cubes over there, cubes or the fourth power. This is still not, there are no interactions over. This is just a propagation of particles. And if you find the energy, if you express this in terms of energy eigenstates, single particle states of definite energy, then there won't be any evolution. Single particle states will just stay where they are. But single particles, definite energy states will not correspond to your wave package localized at a single point. Your wave packet will be distributed over your lattice. Then if you have the cubic term, the fourth power terms, in that case you start to say, okay, if they were absent, in that case they will just have definite momentum, let's say. But when you put those terms, when you put two particles, their momentum will change, etc. Other questions? Okay, now let me pick this one. Also, another reason why I like using this projector is I can copy paste. Okay, so what I want is now I have these lattice points, if you like. I have discrete values 1, 2, 3, but I want to take the limit of a continuous space. I cannot do this with I. Let's say that this is my origin, or if you like, I is equal to 0. Then I can just use, let's say, if here I have the ith atom, its position will be, let me call its position y. And then y will be just, again, I'm just building a simple model. I will assume the spacing is a, so that eventually I will take the limit a goes to 0. And y will be just a times I.
AI? AI?
Yes. There are I sites, a times I.
Imaginary number?
No, okay, sorry. Let me just use, if you like, J. Or N. Now there is then I have xn, for example. This is the displacement of the nth oscillator. Again, what is oscillating? I don't really care. I will be eventually looking at the particle picture. I mean, this chain, you can take them as, I don't know, atoms. In that case, atoms, each atom will be oscillating back and forth. But eventually, when I use this to describe my particles, I will just ignore all that interpretation. This can be some oscillations in some abstract space. I don't even need this oscillation. But I will use these oscillators to construct a framework that I can use to also describe my particles. Now, xn, I will show it as, let's say, phi y. Remember, y is equal to a times n. So rather than looking at the nth oscillator, I will be looking at the oscillator at the position y. Because when I take the continuum limit, I will have infinitely many oscillators, even in a very small interval. So that's why I'm trying to avoid just counting them one by one. But when you show me the position, okay, I can just go and look at the oscillator at that position.
Shouldn't this y equals n should change over time? Because they're vibrating, right?
These are the remember, n is, if you want, n is the equilibrium position. I have an oscillator oscillating around the equilibrium position, if you like. Xn is the deviation of the nth oscillator. So then phi y will be the deviation of the oscillator at the position y.
No, I'm not getting it. Like, if the A is constant, there shouldn't be any interaction between them. They're just moving in a force field, which is provided by normal harmonic oscillator potential. But if you add the interaction term, then the difference between them, the position difference between them should change.
Okay, so
So that breaks the y equals an
no.
equality, doesn't work.
You see, your friend over here is just leaning forward, leaning backward. Okay? But whatever he does, he is the first person on this row. I can talk about the displacement of the first person in the first row. Whatever he does, now he leans backwards, he's still the first person in this row. Now this xn is the displacement of the nth oscillator. Of course, if I solve the equations of motion, etc., xn will depend on time. But so? Phi y will depend on time. So eventually I will have phi y t. You see, y will not have time dependence. His position doesn't change if he leans forward, if he leans backward, as long as he doesn't stand up. He is the first person in the row. But of course, how much he leans forward, he leans backwards, that will depend on time. That is what I call the phi. Phi, if you like, is the how much the person at the position y leans forward at the time t.
I'll just accept and listen to this part again.
Okay.
Hocam, y is just the equilibrium position, and x is the actual position. Is it not?
Y is the particle label, right?
Y is the position label.
Yeah.
And phi of y is the displacement of the oscillator at that position.
Yeah. No, n is the label, and
N and x are the, n and y, they are the same thing.
yeah.
You see, n and y, they are exactly the same thing. N and y. If n doesn't have time dependence, y doesn't have time dependence. I'm just changing names. With one name, it will be easier to take the limit as a goes to 0. What about p? So if this is xn, what about pn? Hmm? How do you define Pn in classical mechanics? Well, let me come to that question later on. There is one thing I want to drive about this term. Let me stick with that term first and come back to, if I want to look at the first two terms, I have to first define what Pn is. Well, this is, if you like, sum over n. Let me put a delta n over here, because delta n is 1. I will be eventually converting this to a Riemannian integral. So I'm summing over n and increasing it 1 by 1. So delta n is 1. Then I have k. Well, xn is, let's say, xn is phi of y. Xn minus 1 then is phi of y minus a. Let me divide by a squared multiply by a squared. I just changed some labels. Now from this one, delta n is delta y over a. So this is equal to, instead of summing over all n, I can also sum over all y's, all positions. This will become my integral. Delta in n is delta y over a. Then I have this a squared over here, k, multiply by derivative of phi with respect to y plus terms of the order of higher order in a squared. They cancel. Okay, k was like the spring constant, right? So if you cut a spring in two, what happens to the spring constant? It becomes, You have this spring.
It doubles.
It doubles.
What was the question?
You have a spring, you cut it in half.
Mm-hmm.
What happens to the spring constant? Does it double or reduce it? It doubles. So if the length gets smaller, the spring constant becomes larger. K is the spring constant, A is the length. So if the length is reduced by 2, if A is reduced by 2, then K will be increased by 2. So A times K will remain the same. It won't change. So what will happen over here is this becomes, let me call kappa A times K. So H1 is now sum over y, delta y. Let's say I'm taking the limit as A goes to 0, K diverges such that kappa is finite. Of del phi by derivative with respect to y squared. Well, the higher order terms in that limit will go to 0. Well, that limit is nothing but the Riemann integral. This is dy, derivative of my field with respect to y squared. Well, there's also kappa. This is my H1. Usually, okay, this is the Hamiltonian. I say this is one dimension, so I'm writing it as the integral over that one dimension of the so-called Hamiltonian density. So this is Hamiltonian. This is my Hamiltonian density. So my Hamiltonian density turns out to be some constant times the derivative squared. This is for 1. Well, this is the term that I wanted to obtain, and I also want to emphasize once more, this is the term responsible for particle motion. Without that term, particles do not move around. That term in our Hamiltonian, or eventually it will be also the Lagrangian, will be this term over here. The derivative terms causes particles to move around. Without the derivative terms, there's no motion. So this is called the kinetic term. Without kinetic term, there's no dynamics. This is something that you will hear quite often whenever you see some field theory discussions. Without these kinetic terms, there won't be any dynamics. And why? Well, basically because of all these reasons. Of course, now we took the continuum limit. Those kinetic terms cause particle to move, to jump in, if you like, to the next side. And then if they can jump to the next side at the next moment, well, they can basically move anywhere.
Can we repeat the part where you produced the kinetic term? I think I read most.
You see, what we had done, I started with this theory, this Hamiltonian. I have the first two terms, and then this term. And then my first argument was that term is what causes my energy packages to go from one oscillator to the next one. So basically, these packages are moving from one point to the other point. How do I know that? Well, I know that that term contains such terms. And in the time evolution, remember, Hamiltonian gives me the time evolution. If you look at the time evolution, what will happen is at the next time, this operator will just create, annihilate packages at a given site and create them on the next site. Whereas this one will annihilate an operator at a package at a given site and create another one on the previous site. So if you have one package at a given moment, at a given location, at a definite location, in the next moment, it can be either in the next site or on the previous site. So this is basically how the packages will be moving in this simple model for the simple Hamiltonian. So those terms causes the derivative. Those terms cause the particles to jump to the next site or the previous site. Of course, if you allow a particle to jump to the next site, in the next moment it can jump furthermore, and so you have all these jumping system. So the particle can just move forward, it can move backward, it can go anywhere. Now, then what we did was, now this is what we call a field. This is our field. So a field, in the mathematical sense, is basically a function. So it just assigns something at every point in space-time. That is what we call a field. So here, this phi, you give it the y-coordinate, give it at any point, it gives you some other number, which in this sense corresponds to the deviation of the oscillator from the equilibrium value from 0. And now we said that, okay, that term, which is responsible for the motion of the particles, the particle moving from one side to the other one, will give me eventually, when I take the continuum limit, this term. Well, typically what we will do is we will define still another field. We will say that it's just a normalization, which will be square root of kappa phi or square root of 2 kappa phi, so that H1 will be 1 over 2. This is the conventional normalization. You see, if you have a Lagrangian or a Hamiltonian, let's say a Lagrangian, if you just multiply it by this constant, it basically describes the same physics. So
Why there is a kappa there?
Hmm?
You know, we define kappa. You know why?
Kappa. Well, I mean, when I was writing this term, there is a spring constant over here, which basically tells me how strong successive points are coupled to each other, essentially. And then that term got multiplied by the lattice spacing, which gives me kappa. Now, I can get rid of that kappa by a redefinition of my field. This doesn't get rid of kappa completely, because remember, if I make a redefinition here, there are other terms. I have to redefine the other terms. So what will happen, for example, if kappa is very strong, that means particle can easily move back and forth. I would expect that such a system to be massless or have a small mass. Large kappa would, I mean, if we look at the other terms, will correspond to smaller mass.
How we interpret it in the condensed matter side? How we interpret it? So
Yeah, in the condensed matter case, I don't even need to define a kappa because they're already discrete.
They're already.
Discrete. I mean, here I had to define a kappa because I'm taking the limit a goes to 0. If I would like to have a finite term, k should go to infinity, but that's also what I expect from this spring analog. So a should go to, as a goes to 0, k should diverge in such a way that kappa remains constant. But if you have finite a, kappa is just k. Large kappa means large k,
What's
small
supposed to
kappa
mean
means...
that if the k spring constant goes to infinity, then there is a, you know, they are easily moving that, you know, when it goes to infinity. And what's supposed to mean that there is no any, I mean, it's all along a field, something?
Well, let's see. What will so you are asking that, let's say that, let's keep everything finite. A is finite.
No. As I say, k goes to infinity.
But you see, if I take the limit a goes to 0,
Uh-huh.
k is not, does not appear by its own, on its own. K always comes with a in the continuum limit. So what will have a physical importance is a times k. You see, what is happening over here is you are saying that k goes to infinity. But then, you see, if xn minus 1 goes to 0, then k goes to infinity doesn't really have much influence. And assuming that the energy will be minimized, k goes to infinity will basically tell me that xn should change very slowly with n. So k becoming very large basically tells me that xn should change very slowly. In fact, that is understandable also in the continuum limit, because in the continuum limit, xn and xn minus 1, they are practically at the same point, n and n minus 1. So the displacement there has to be the same, more or less. What will be important will be this
Somehow it's a
kappa.
uniform circle, like a uniform circle.
What will be important will be this kappa, not a, not k separately.
Does K depend on how firmly the atoms are put together?
Well, k will be determined by interatomic potential, whatever. It will depend on the properties of, in a solid state context. K will be a function of their interatomic potential, whatever that is.
They always like immersion with A.
With what?
Is there any inverse relation between A and K?
Well, you see, if you want to go to the condensed matter analog, A is also fixed. I mean, you cannot really say A is small or A. I mean, you cannot play with A. Now, here in this problem at least, we are just playing around a bit, playing around in such a way that eventually we are taking certain limits such that still we have a sensible theory. But for example, even in condensed matter systems, I mean, this you can also use for, let's say, to describe phonons of large wavelength, because they won't see the atomic structure. So you can take the continuum of it. But even in that case, you have to take A to 0 in such a way that K will go to infinity such that kappa will be finite. Well, if you want to apply this to an actual system, A is finite, K is finite. Well, you will measure A, you will measure K, you will obtain their product and use that number for your kappa. And as long as you restrict yourself to large wavelength, well, your continuum theory will still give sensible results. Other questions? Let's go to the momentum. Well, first of all, to go to the momentum, I would rather go to the Lagrangian than stick with the Hamiltonian. Hamiltonian, okay, we are used to using Hamiltonian in quantum mechanics, but in field theory we will be using with Lagrangians also because of Lorentz symmetry. Because Hamiltonian is energy, it's not Lorentz invariant, it has different numbers at different reference frames, but Lagrangian has the same value in every reference frame.
So Lagrangian is more fundamental than Hamiltonian.
What do you mean by fundamental?
I just heard this question from a seminar, and
if you say that being more fundamental means being invariant under Lorentz transformation, being the same in every reference frame, fine, yes. But I mean, sometimes I don't think we really know what is meant by fundamental. At least in most systems that we will study. Well, in all systems that we will study in this course, if you have a Lagrangian, you have a Hamiltonian. If you have a Hamiltonian, you have a Lagrangian, whichever one you prefer. Lagrangian will be easier in most cases, as in this one. So Lagrangian of my system, I'm looking at the same system. What will change will be, Lagrangian will be 1 over 2 xi dot squared plus 1 over 2 omega squared x squared, no, minus 1 over 2 k xi minus xi minus 1 squared. Now, of course, since I'm considering the time dependence also, the time derivative, I will put in this definition xn I will identify xn of t with phi y at the time t. So my Lagrangian, let me call this part L0. L0 will be sum over n 1 over 2 del phi by del t squared. By the way, I made a mistake. I mean, let's forget about this phi tilde for the time being. It will have a different meaning. Minus 1 over 2 omega squared phi of y of t squared. Remember, n is y. Well, let me also make it explicit. Rather than summing over n, I'm summing over y. Let me introduce the delta n, which will be delta y over a So L0 is sum over y of delta y 1 over 2a squared minus 1 over 2 omega squared phi squared. Let me put the a over there. So I have 1 over a dy. I'm taking the limit a goes to infinite, 0, but keeping the overall 1 over a for the time being, because probably my definition of kappa was also not, strictly speaking, correct. This is dy, 1 over 2 del phi by del t squared minus 1 over 2 omega squared phi squared. This is my L0. My L1, the other term that I calculated was basically this one. dy ka del phi by del x squared. So any questions up to here?
Can you move L1 to be without the minus 1, without the minus sign, or with
Okay, let's go back. H is plus 1 over 2k xn minus 1. That is the potential term. That is with a plus sign in the Hamiltonian. The potential term appears with a minus sign in the Lagrangian. So that is why I have a minus sign over here. L1 is actually equal to minus H1. Okay, conventionally, what we do is we define the normalizations such that the coefficient of the derivative of phi with respect to t squared, this term, is just 1 over 2. So that's the convention. You see, I have that 1 over a term over there, which I don't like. It diverges in the limit a goes to 0, but I can change my normalizations. I'm free to do that. It doesn't change the physics. So I will define phi tilde as phi over square root of a. So my Lagrangian density, I'm not writing the y integral. I will just write what appears inside the y integral, will be 1 over 2 del phi tilde by del t squared minus 1 over 2 omega squared phi tilde squared. Then I have minus ka squared del phi over del x squared. This is my Lagrangian density. This is phi tilde. Now, in our next lecture, what we will look at is the Lagrange. Look at this Lagrangian.
Ka squared, just the second term there,
Yeah.
minus Ka squared.
Yes. Only a is squared, because you see, this tells me that phi is square root of a phi tilde. So here I already have 1a from this term. I get that second item. Well, we will see that this Lagrangian, I see, they basically look the same, with k times a squared identified as the velocity v squared. Well, this will describe waves which move with velocity v, some kind of waves.
Madam, can I ask something? We choose coefficient. We want to make coefficients as 1/2 because it is the convention, or is it because we want the next term to be canonical?
What do you mean by canonical or convention?
I mean, by convention, you can pick A to be 1 to have 1/3 in front.
Mm-hmm.
But in field theory, there's this canonical kinetic term in which you have to have 1/3 in front of it.
That's the convention.
Is it a convention?
Yeah.
Or is it something?
No, it's a convention. I mean, I can always multiply my Lagrangian with a constant. Hmm? That's an overall constant. It will describe the same physics. That will change this coefficient 1/2. Well, of course, if you change those coefficients, you also need to modify all the other results that you are using. And also, is the convention to have the time derivative coefficient 1/2 or the del by del x squared 1/2?
Del by del.
Hmm?
Del by del.
Probably del by del x.
Del by del.
Yeah. I will also get rid of that v and move it to the first term. It's just a changing normalization, that is nothing else. But the interpretations, I mean, one is just the conventions. It's up to you. I mean, whether you want to have the first term coefficient 1/2 or the second term coefficient 1/2, it's just completely arbitrary. You can choose whichever one you want. But when you try to start, just like normalizing wave functions to 1, that's also arbitrary. You don't have to normalize quantum mechanical wave functions to 1. But if you change your convention, then the interpretation also changes. So those two should be consistent. Your conventions and interpretations should be consistent. Next hour, I will probably move that v to the first term. Now, any last questions before you go?
What was the v? What was the v?
For the time being, nothing, just some coefficient over there. You see, we are taking the limit a goes to 0, and I want the k a squared to be finite, so k should diverge somehow such that k times a squared has to be some finite number. If I would like to have some finite a equal to 0 limit, a sensible a is equal to 0 limit, I should better have that coefficient finite. It can be, v can turn out to be 0. It will turn out to be the propagation wave, the velocity of the wave in this one-dimensional medium on the string.
The previous Lagrangian we wrote eventually it's on 1 plus 1 dimensional, right?
Yes. You see, this one over here, this Hamiltonian, or the corresponding Lagrangian, when we take the limit a goes to 0, it just became a one-dimensional space, one-dimensional string if you want. And you can just imagine, you have this one-dimensional string, you are just oscillating it up and down. So if you are consider it as a string which you vibrate up and down, it's actually a two-dimensional problem. You have oscillators in one dimension, and those oscillators are oscillating in the other dimension. But since we are looking at the particle interpretation, we will look at this problem as I have the quanta of these oscillators are my particles. They can move along this line. And this Lagrangian is basically describing the propagation, the motion, the dynamics of that, the quanta on that one-dimensional space. Within this picture, it's nothing but just energy packages moving along this one-dimensional space. And we will see what V is. So see you next hour.